Okay, so today I'd like to have you guys do some actual math problems with relativity. I just want to remind you that Einstein's special relativity is based on frames of reference that are moving at a constant speed. It's all predicated upon the idea that the speed of light is the same regardless of your frame of reference. So if you have two people who are in different frames of reference, they will both measure the same speed of light, but they will disagree on things like how much time passes. So let's see how this works out. Okay, we had our ship view, we had our Earth view, we had the ship itself. We saw the person on the ship sees this light beam go straight up. The person on Earth sees it go on a diagonal, and the ship itself moves a certain distance horizontally while the light is heading toward the top. All of relativity in terms of the math revolves around some simple ideas: Pythagorean's theorem for the right triangle, and velocity equals distance over time. Okay, and I think you guys were at this point right here, and then I asked you to derive the equation to relate time on the ship to the time on Earth. So the first thing you were supposed to do was solve it for y and square it, solve it for x and square it, and then plug the x squared and the y squared into your equation. So when you do that, you should have gotten this. Then the next step, you were clearing the fraction. So you bring the TE over to this side. It looks like that. Then you wanted to get rid of the square root, so you squared both sides. Then you wanted to get all the terms with TE on the one side. Then you wanted to factor out the TE from these two terms. Then you want to solve it for time on the ship, so we bring the c squared over. We then simplify, so c squared over c squared becomes 1. And then finally we get rid of the squares, and we're left with time on the ship equals time on Earth times this quantity. This equation is profound, even though it came from very simple ideas like Pythagorean theorem and velocity equals distance over time. And that idea is that if you're in two different frames of reference, time will pass differently in those frames of reference. So TS is the time measured by the guy on the ship, and TE is the time measured by the person on Earth. They will not see the same amount of time go by. How do we know that this is even real? So there are a few different examples where humans have actually seen this happen. One is a change in half-life. So if an object has a certain half-life, let's say 5 minutes, when it's sitting right next to me, if we take that same object and put it in a different frame of reference and have that frame of reference moving relative to me, we will see the half-life change because time is traveling differently in the two frames of reference. One frame is measuring more time and one frame is measuring less time. The change is not random, but the change exactly follows that equation that we derived. We can also see this with real clocks. If you have a highly accurate clock, the kind that we would have for our U.S. Bureau of Standards and the military, these highly accurate clocks, if you have them right next to each other in the same frame of reference, they will tick off time together and they will stay synchronized. But put one of those clocks in motion on an airplane or in a satellite or any kind of motion relative to the other clock, and the two clocks will no longer synchronize. One clock will have time pass quicker than the other. Not randomly, but again, just like that equation that we had derived. The final example is a place where in real life they have to account for these relativistic effects, and that's in GPS satellites. Those satellites that are in motion relative to the Earth are going to have the time tick off differently. and they have to account for that change in time, or else the GPS satellites would send out signals which we could not synchronize with our Earth GPS units. Within a matter of just a few hours, our GPS would go totally haywire as these clocks no longer stay synchronized. We have to teach the clocks how to account for the relativistic change in time because of the relative motion. So, to show you guys how to do these math problems, imagine you have a ship that's moving at 0.5 c. What does that mean? It means half the speed of light. So you'll see that with high speeds. Instead of giving a big long number, they'll give it to you as a fraction of the speed of light. It says if an observer on Earth measures 5 years past, how many years will pass on the ship? So what you do is you take that 5 years on Earth and you put it in for TE. You take the 0.5, the speed of light, and you put it in for the velocity, and you're solving for how much time passes when we view the person on the ship. Okay, there's two ways you can attack this. You can use actual numbers. So half the speed of light goes in for the velocity, the speed of light goes in for c, and you solve. Or it's oftentimes easier, instead of putting an actual number in there, to do something like this, 0.5 c squared. So when you do that, you get 0.25, I squared the 0.5, times c squared. I now have c squared top and bottom, so they can cancel. And you're down to time on the ship equals 1 radical 1 minus 0.25 time on Earth. You plug in and you find that only 4.33 years went by on the ship. What this means is we're watching that ship go by us, 5 years pass on Earth, only 4.3 years pass on the ship. Time on the ship is slower than time on Earth by a good bit. If we make the speed of the ship even faster, again, I would jump right to this final part where I just plug in 0.9 times the speed of light. I square that, I work it out, and it shows that only 2 years went by on the ship. So you can see the faster the ship moves, the slower time moves. If we could bring our ship all the way up to 0.999 c, 99.99 the speed of light, we would get 25 days. 5 years pass on Earth. 25 days pass on the ship. The person on the ship ages by only 25 days, whereas we age by 5 full years. Okay, what would happen if the ship was traveling at the speed of light? Well, we saw the faster we went, the slower time went. So what would happen if we hit the speed of light? Imagine plugging in the speed of light here. So you'd have speed of light squared divided by speed of light squared. That gives you 1. 1 minus 1, 0. Square root of 0, still 0. And what that means is no matter how much time you put in here, you'll get 0 amount of time passing on the ship. What that actually means, again, you can see it here, what that means is that time on the ship has stopped. When you travel at the speed of light relative to another frame of reference, the person in that other frame of reference is going to see time stop for the frame of reference that's moving at the speed of light. What would happen if the ship was traveling faster than the speed of light? People think, well, if time stops, maybe time starts going backwards. However, we can't justify that. If we plug in a number greater than c, we're going to have 1 minus a number greater than 1. That's going to be a negative number. And when you take the square root of a negative number, we get imaginary numbers. We don't know what that means. That does not mean that we're going backward in time. It means there's something wrong that happens when we exceed the speed of light. In future days this week, you'll see why exceeding the speed of light can't happen. But even if it could happen, this equation does not say that time goes backwards. So we can slow time down, we can stop time, but we cannot make it go backwards. If you look at this graphically, fraction of the speed of light, you'll notice 5 years go by if you're at rest relative to the Earth. If the ship is traveling at 25% the speed of light, there's hardly any slowdown in time. Half the speed of light, there's a pretty significant slowdown in time. And by the time you hit the speed of light, the time goes to 0. So you guys can see that this is not a linear thing, but it becomes more and more dramatic the closer you get to the speed of light. Okay, so finally, if you have a problem like this, and you will have one like this, if the number is small enough that it's not like close to the speed of light, just plug in normal numbers. So plug this in as your v, plug in 3e to the 8th as your speed for light, and be very careful that your calculator doesn't round away your number. So be careful, write out all your digits, otherwise you're going to get an error or you'll get no change when you work through this. All right, so work it through carefully. Okay, your problems today hopefully will not cause you too much problem. I'm going to give you all of tomorrow to get this done, and also Thursday, so you'll have Wednesday and Thursday to work on this. These problems will be due at the end of the day on Thursday. You do not need to show me your notes because we've already covered all these ideas. I just wanted to talk to you a little bit about how to use the equation before you start the problems. So good luck. Let me know if you wanted to give you a quick update on the garden. You could see the potatoes have not grown much since the last update. I think the frost that hit them in April might have caused them to not grow the way they should. See, the carrots are growing really well. See, I got my strawberries protected from the bugs because they're starting to turn red, so that's very exciting. I put in a new bed. I'm going to put a tomato in here. I have some basil. See, my little broccoli plant that I showed you guys before is just about ready to be harvested. My eggplant is okay. Some squash growing, some turnips and some kale, more turnips. You can see some of my spring plants are starting to bolt, so they're not going to be edible anymore. Again, I got some beets going in that are looking good. Lots more turnips, and you can see some of them are actually bulging at the seam, ready to be picked. The asparagus is pretty much done. Spinach is bolting, but the lettuce looks great. Again, look at all these delicious lettuces. And again, more plants that have bolted and are done for the year, but they look very pretty. You could see that I have, my peas are nowhere near what they should be. They keep getting eaten by a groundhog. So I put in some protective fencing to try and deter him from getting to the peas.